Hello, everyone, and welcome to the March 2026 Link Tech Talk. My name is Olivia Lynn, and our co-host is Colin Orion Chandler. We're both members of Link Frameworks, I as a software developer, and Colin as a project scientist. I'm at Carnegie Mellon University. Colin is at the Dirac Institute and University of Washington. Link Tech Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, here we highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss the efforts of interest in the analyses of LSST data. Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific, 1 p.m. Eastern. Drew Oldag is a Link Frameworks principal software engineer, technical lead, and self-described golden retriever at the University of Washington. He studied physics and astronomy as an undergraduate, focused on infrared instrumentation before discovering the joy of writing code. He spent a decade in industry before returning to academia to work on the Link Frameworks team, building software to meet the scale and complexity of the Rubin Observatory data. For the talk, please ask questions in Zoom or in the Link Tech Talks channel of the Discovery Alliance Slack. On Zoom, you can type questions into chat or raise your hand. As a friendly reminder, these talks are being recorded and they will be posted on our YouTube channel. With that, Drew, please take it away.
Cool. Thank you so much, Olivia. Yeah, I really appreciate the introduction. Very kind of you. Um, I also wanted to say, there are a relatively few number of people here, so feel free to just interrupt me at any point. I'm happy to take questions in the midst of the talk as well, if there are any questions. Um, yeah, so I'm going to be talking about Hyrax today. Hyrax, as the tagline says, is a low-code solution for rapid experimentation with machine learning and astronomy. We're experimenting with a few different taglines, so if this one doesn't resonate with you, please let me know and we'll modify it. But uh, this is this is a tool that we've been developing for about a year and a half now. It's getting to a state where it is starting to congeal and stabilize, and we're looking to expand the number of people who are interacting with it so that we can identify the proper directions to take this in the future. With that said, I'll jump into a little bit of the sort of standard preamble, motivation, why we got into this in the first place. Um, so yeah. Yeah, in terms of motivation, I think probably none of this will come as a huge surprise. Survey scale is getting much, much larger in the very near future. The number of large surveys that are coming online in the next roughly decade are just going to absolutely dwarf the astronomical data that was available prior to this. Traditional analysis techniques probably aren't going to scale up to that level of data, and new techniques will be necessary in order to handle the volume of data coming in. One of the forerunners and likely candidates that would help would be machine learning. Machine learning, though, comes with a lot of caveats, and in particular, lots of bottlenecks associated with developing, scalable or production level pipelines. And so, just sort of running through this diagram here on the right, almost at every step in a machine learning pipeline, there exists a bottleneck. I mean, just right off the bat, acquiring data is typically very challenging. Again, because of the volume, because of the complexity of the bespoke systems for every survey, every survey is different. Acquiring data is going to be challenging each and every time. And then, of course, once you have your data, you want to start training models and experimenting with different models, keeping all of those models organized, the accounting there, evaluating the performance of them, is just another set of boilerplate code that you have to write in order to do that. Once you've got models that you feel are performing well, there's another layer of like running inference and visualization with those so that you can actually push large volumes of data through it and see how it's performing there. If you want to do any sort of similarity search, that's another layer. And then hopefully at the end of all of that pipeline, you get to the point of discovery, which is where the real science happens. And so what you see with all these bottlenecks is that you put in a lot of effort uh, to get to a discovery, and the vast majority of that effort does not accrue to your CV. It is not something that you write about in the paper. It's just sort of boilerplate required infrastructural code that you have to write. that doesn't necessarily help your career out all that much. So those two things combined pushed us toward creating Hyrax. We wanted people to be able to focus on the science, focus on the analysis side of things, not have to deal with the infrastructure code. And so diagrammatically on the left here, that's what we're trying to demonstrate here. So in the center, in the core, is that nugget of ML code, the exciting part of like building a model architecture and then doing something with that model architecture. But all of the big blocks around the side are the things that go along with creating machine learning pipelines and doing science with them that aren't necessarily as exciting but have to be done. So think about things like tracking your configuration for any given run, or monitoring the status of a given run, or comparing your models, or scaling from your laptop to your department server to your local HPC, whatever that may be. All of those things are steps that require significant effort, but don't necessarily, get you to the science per se. So some of the high-level points that Hyrax tries to focus on are one, effortless scaling. Like we want to make it very easy for someone to experiment on their laptop and scale up from 0 to many GPUs without having to make any code changes at all. It just happens completely under the hood. Um, we've developed survey-aware data downloaders. What we mean by that are, very rapid ways to acquire HSC and LSST cutouts. We've got more to come, just haven't built them yet. We put a lot of effort into keeping data organized once it enters Hyrax. So all of the data, all the configurations, all the results, everything is tracked and well organized. It's all extensible. What we build on Hyrax is not meant to be the end-all be-all of what can be developed with Hyrax. What it is meant to be is a platform for you to build on top of. So it's all open source, it's all extensible. And then we've got lots of diagnostic tools, built-in visualizations, those sorts of things to help you along the way. So just, again, trying to take some of the edge off of the effort to do an ML project. So before I get too much deeper into what Hyrax is and more of the technical side of it, I wanted to talk a little bit about some of the design decisions that we made when we were first getting started. These have guided our development throughout the course of this. And so one of the first things is choose open source first. There are many tools available for helping with machine learning in general. We do not take so much ego as to assume that we can rewrite all of that and do it better than what's already been established. So if there are open source tools that already accomplish particular goals and they've been well tested and well established in industry, then we would definitely use those first, incorporate those into the Hyrax framework before we implement them ourselves. But if open source implementations don't exist, then of course, yeah, we write that code. And so some examples of that are, bespoke downloaders for LSST data where we interface directly with the butler, or some of the visualization tools we've written to help scale to the level of LSST data. We want to make very sure that we decouple our data from our models. So within the machine learning community, it is not uncommon for the data loaders, the data acquisition tools, and the model training and the model analysis to all be grouped together in maybe one giant notebook or one giant Python module. We wanted to encourage users to separate the data from the models because when you do that, it means that the data becomes reusable in multiple different ways, and the models become reusable in multiple different ways as well. So the data is no longer tied directly to the model per se. For instance, say you have a model that you wanted to train using LSST data, but then extend it to Roman data. You can train with LSST data, but because your model is not tied directly to that, once the model is trained, you can then pull in a different data set and feed that data into your model. Because they're decoupled, it means that you can do that very easily as opposed to rewriting your model essentially from scratch or rewriting a lot of boilerplate code to funnel the data in. So we'll get more into that in a little bit. We wanted to support lots of different ML frameworks right out of the box. We started with PyTorch and have expanded to Onyx. In the future, we anticipate supporting TensorFlow, JAX, or whatever the most needed ML framework might be for the given use case. And then from the early days, we decided we weren't going to do any command line arguments. Hyrax is a tool that's meant to be used either in a notebook or from the command line, so it can be used in like Slurm systems on HPC systems. But we wanted to shy away from command line arguments because there are lots of things that could potentially go on the command line as an argument, and that becomes this uh, you know, incantation that becomes very challenging to reproduce from one person to the next. And so we wanted to use a configuration system via a file-based configuration system as opposed to a command line argument-based configuration system. We'll talk a little bit more about that as well. So those were kind of the high-level design decisions. Um, let's talk a little bit about what Hyrax is. So I've talked very abstractly about what it is and what it's supposed to do. Um, at the very highest level, I'm going to say Hyrax is organized into verbs. And when I say verbs, what I mean are like collections of complex actions that can be linked together to form an ML pipeline. So you can think of train as a verb. Under the hood, training is going to be doing things like loading the configuration file, setting up your results directories, loading the data sets that are required, getting your model loaded, et cetera, et cetera. All the things that are required to do a training run, the single verb is going to take care of on your behalf. So you as a user specify that you want to run training, and you tell it how to run training via a configuration file, and then Hyrax takes care of all of the fine-grained stuff that might be kind of annoying to handle on your own under the hood. And so when you link verbs together, you get, maybe a little bit of a pipeline. So, a contrived example here at the bottom of the slide is, well, we'll create an instance of Hyrax. We'll ask Hyrax to download. Again, we'll specify via configuration file what gets downloaded. Then we'll ask Hyrax to train. Again, with the configuration file, we tell it how to train, number of epochs, loss learning rate, et cetera, run inference, run visualization, those sorts of things. And these verbs can be slotted in and out and moved around as necessary for the user to build whatever pipeline they need to build. So I've mentioned multiple times now configuration system, foregoing the use of command line arguments, those sorts of things. So I wanted to kind of dive down into that a little bit. I know that configuration systems may not be like the most exciting thing for many astronomers or many people in general, but you've built this kind of complex system that's worth understanding how it works so that you can get a sense of the utility of it. So it's a stacked configuration system where Hyrax provides what we believe are a reasonable set of default values for every possible configuration value that Hyrax is aware of. The user can then step in and provide a user-specific configuration for their specific thing. So they don't necessarily need to redefine every single default value. They can redefine or respecify only the values they're particularly interested in. And then Hyrax, when you instantiate it, will take the default, layer on top the user's specific configuration, and create a runtime configuration that is the merging of those two. And I mentioned earlier that Hyrax is extensible. So what we mean by that is that external libraries can develop components for Hyrax to use. They also provide default configuration files. And so the extra caveat here, this layer in the middle of external default configuration layers on top of the Hyrax default. And then again, the user can specify specific changes for this external configuration as well. At the end of the day, what you end up with is this fully hydrated configuration file that specifies everything that Hyrax is supposed to do within a given verb. This can be off-putting potentially for some people because one of the bits of feedback that we got was that it takes the sense of writing code and pushes it from Python modules or writing code and into a configuration file. And yes, that to some extent is true. You're not writing code in the config file, but where before you might have added a few new parameters to your method, now instead you look to the values stored in the configuration files. The reason we do that is it is much easier to holistically track all of the configuration settings for a given run when everything is in a single file. And those files can be made completely immutable at runtime so that once the run starts, you know that the configuration is locked and you know exactly what went in to begin with. All the configuration files are saved on the output so that you can go back and reference it. And by loading a given configuration file, you can reproduce a run in its entirety very reliably. And so that makes it easy to, for instance, collaborate with other users. You could just share the configuration file and permission to the input data, and they can pretty reliably reproduce the runs that you were doing on your local machine. It also makes it pretty easy to like scale up to bigger machines too. You just copy your configuration file from your laptop to your HPC system, and then you run from, instead of your laptop, now you're running on 100 GPUs or whatever it may be. So it's got a lot of benefits. I wanted to talk a little bit about how data moves through Hyrax as well. Again, I know this is maybe a little bit more technical than people want to dig into, but I am here, I'm in charge, so I'm going to take advantage of it. Um, when I was talking about separating data and models, the way that data moves through Hyrax really clarifies that. So what you see here maybe looks a little bit complicated, but we'll just move left to right across the screen. Starting with the colored boxes that are labeled data, imagine that as just data on disk. It could be any modality of data. It could be flat files. It could be images. It could be tabular, whatever it may be. Hyrax supports what we call dataset classes. These are uh, the bits of code that know how to read data off of a disk and provide it to Hyrax to process. Right? So it is, specific to the data that is on disk and returns NumPy values. And we chose NumPy as a sort of consolidation point because the vast majority of the field is familiar with NumPy. It is not specific to any ML platform, and it makes for maximum reproducibility and understandability. All of that gets fed into what we call the data provider. So this is a central uh, uh, tool that allows the user to feed in data, specify the exact data that they want, and output that data for the rest of the Hyrax chain in a very structured way that makes it easy to work with. There's some magic that happens after data provider that I didn't want to go into just because I didn't want to overwhelm everybody. But ultimately the data gets passed to a boundary layer called prepare inputs. This is a little method that lives on each model. And the job of this prepare inputs method is to modify the form of the data from a dictionary of values into whatever the shape is that's required for that particular model. So in the ideal scenario, when a user is experimenting with Hyrax, they can modify just 2 points in the flow. They can specify the data they want with their config.toml file, and they can make modifications to their prepare inputs method to make sure that the data going into the model is exactly the right shape for the model. And the asterisks here just indicate that these are saved at the end of every run to make sure that, again, full reproducibility. I'm going to put a little extra caveat on that. The reason we just save these files as opposed to hoping that the user will use like a version control system is because it's just easier. It's very challenging for a user to remember to hit git commit at the end of every small change to prepare inputs to be able to track their changes. Instead, we just take care of that on the user's behalf. Right. Um, I wanted to talk just a little bit more about this config.toml file. There's a lot there. I'm going to go even deeper into that one because this is the part that I really truly love. So uh, we've created what we call HyraxQL, Hyrax Query Language. It is inspired by GraphQL, which is an open source data query language typically used for the web. The point of GraphQL is that it makes it very easy for web developers to make modifications to the type of data they request for the front end without making modifications along the entire chain, the full stack of their web platform. So they don't have to make modifications at every single layer. They just change what they're requesting. The same is true here in Hyrax. So HyraxQL allows you to One, very crisply define exactly what data you want to pull from disk to use for your model. The other thing it does is it allows you to combine data very naturally. So a very typical scenario in machine learning is when you have two different data sets that you want to use in the same model. You duplicate on disk. You take this data set A and data set B, and you merge them together in some sort of pre-processing thing that you run one time. And then now you have data set C that's like the combined A and B. With HyraxQL, you don't have to do that. You just do it in real time. You say, you specify you want data from A and you want data from B, and you want them to be merged and passed to your model. So that's the hand wavy definition of it. But I'll go through the crisp scenario that's described here on the screen. Um, Again, on the left, you have data on disk. It's in a directory called data. This particular hypothetical data has, FITS files and some sort of tabular data that's got, four different columns, A, B, C, and D, and you want to work with that. So as mentioning before, Hyrax has this concept of dataset classes. So that's the green box that you see in the middle. A dataset class is going to be comprised mostly of getter functions, or functions that you'll see have get underscore something at the beginning. So in this contrived example, we've got get image and then get A, B, C, and D, one each for each of the different columns. And what each of these methods will do is, given an index, will return the corresponding field from the data set. So that may be the image and the FITS file format, or it may be the value from one of the columns. That's what's going on here. And then within the data provider on the right-hand side, it has the copy of the user's runtime config that has the data request. So here we have specified that we want to use my dataset class. Again, it's this green box. And we've specified where the data is coming from, the actual place on disk. And we're specifying the fields that we want. So we don't necessarily want all of them. We just want image and then columns B and C. And we're going to say the column B is the primary ID field. And we're going to do an automatic split on this. We're going to say we only want 80% of this, a reproducible 80% of that. And so now data provider has all the information that it needs. It has the configuration, it has the dataset class, and it knows where the data is on disk. And so in this instance, if we tell data provider to please retrieve index 1, what we will get back is a very well-structured dictionary that has the training data for my data with the B fits file from index 1, as well as the value 6 and 7 for columns B and C. So again, I hate to harp on this, but this makes it very easy now for the user to say, well, actually, I want column D as well, or I want to combine this with another dataset class and get another more complex version of the data back. So that's what's going on there. All right. I've talked a lot at high levels. Let's do a demo. It's always risky. This is going to be roughly the Hello World demo for Hyrax. It's based on a very common ML algorithm. So we've implemented a simple convolutional neural network. We're going to be classifying the CFAR10 dataset. If you're unfamiliar with the CFAR10 dataset, here's a quick example here on the left-hand side. It is a collection of color images. All of them have the same pixel scale. X and Y values are the same number of pixels. 10 different categories, all of them well labeled, all of them well established. And the goal is to create a classifier that can classify them with some level of accuracy. So give me just a moment here to change what I'm sharing. Right. So I won't actually run it this time just to save you from watching it. But what I want to get across here is the level of encapsulation that Hyrax provides. So here we're going to create our instance of Hyrax. So that's simply importing Hyrax and calling the main Hyrax class. When you do this, when it's called this way, you get all of the default values from the default configuration, and Hyrax instances is ready to go. In this particular case, we do need to specify a model. So we will set the config model name to be Hyrax CNN. So this is, again, our built-in convolutional neural network. And then we're going to specify the data set. that we want to use for training. So as we saw a little bit earlier, we've got this pretty structured way of saying that we want to use the CFAR data set that's in this location. We're interested in images and labels for training because we need both of those values to train. And object ID is our primary ID field. And we set that on the config too. Then we train the model. We call hyrax.train, and what comes out the other end is a trained model. In this case, I won't show you the logging output, but you have to trust me when I say logging comes out and the model ends up trained after 10 epochs. We can immediately take that trained model and feed it into inference. We'll update our data set first to make sure that inference is provided an honest version of it. So one thing you'll see is here for training, we asked for the label. And in inference, we do not ask for the label. We just ask for the image and the object ID. So we're trying to keep it honest. We update our configuration again, and we run infer again. Hyrax is meant to be pipelined together. The reason we can get away without having to specify which trained model to use is because it will automatically go and look at the most recently trained model by default. We can, of course, specify, no, use this one specifically, but in this case, it just makes it very smooth and natural. You don't have to specify it because we're just going to use the previously trained model. Now, everybody loves a little bit of plotting code. I don't love a little bit of plotting code, but that's what's going on here. The output of the CNN is a 10-dimensional vector. We're just going to, in here, identify which index in each of those vectors is the largest value, and we're going to use that as the predicted class. And we're going to open up the actual test data set so that we can actually get at the label so we can do true, false, positive, those sorts of things. And then we'll lean on scikit-learn a little bit to plot our confusion matrix. And at the end of the day, what you see is this, our overall accuracy for our test data set, in this case, 47%, which doesn't sound great, but recall that this is 10 different classes. And so if this was just random chance, you would expect an accuracy around 10%. So our model has been trained, it has learned something, and then when we run inference with it, we get an accuracy of about 47-ish%. So not too bad. This is the goal of Hyrax, to get as much of the boilerplate code squared away and recall all the stuff that's going on in the background, the data set loading, the configuration saving, all of the training loop is all obscured away from you, so you don't have to deal with it. All of it's taken care of on your behalf. So that's what's going on there. Now I want to hop back over here. So that was okay. Hello world. Maybe not the most exciting thing, especially given this audience. I understand that many of us are scientists, not myself personally, but let's look at something that's a little bit more sciencey so that it starts to feel a little bit more applicable to maybe the type of things that you actually do. So in this demo, which I actually will run because I think it's kind of impressive to see it run start to finish in the amount of time that it takes me to talk about it. We're going to train an autoencoder. So an autoencoder will is typically used in unsupervised ML algorithms, and it will take an image, squish it down into a latent space, a low dimensional representation, typically on the order of like 64 to 128 dimensional vectors. And then there is a decompress or decode state that will take the compressed version and expand it back out. And that's how you calculate your loss function. So you give it an image on one side, it compresses it, decodes it on the other side, and then you sort of compare and contrast what comes out versus what went in. That defines your loss. In this particular example, we're going to be working with a small sample of HSC data. We're going to be using train, infer, and UMAP, and we're going to discover some classes in unsupervised data. So pardon me again while I switch screens out and we look at this one. So again, I'm just going to, it's always risky running in real time, but we're just going to run it and see. I think it's going to work. I'm pretty confident it's going to work. All right. We're going to import a couple of things. We're going to acquire the sample of HSC data. We've stashed it on Zenodo for convenience. If you're interested, you're welcome to go grab it. I can show you exactly how to get it later. One thing I want you to watch here on the side is that these are the time-stamped output results as they're coming through. So train was started, let's see, yeah, just about 15, 20 seconds ago. Uh, the output of inference just popped in. UMAP is happening now, but we'll get to that as we scroll through here. So again, we'll initialize Hyrax just as we did before in the Hello World version. Here we'll specify our data directory, the model that we want to train. We're going to train for 20 epochs, specify the batch size. We're going to specify the different subsets of the data that we want to use. So the HSC 1000 data set that we're calling it has about 1,000 samples of HSC data in R, G, and I bands. Um, Here we're specifying that we want to take an 80-20 split for training and validation, and then we're going to train it. So this is the output of training. So we've got, we call Hyrax.train. It's telling us we're going to train our autoencoder V2 model. It's telling us what data sets we're going to be using. It's telling us that our data loader is prepared and ready to go. And the total training time was 13 seconds. There's more information there, but we won't dig into it too much. And if you're interested, here's the results of training that we just did. So it doesn't look amazing, to be honest, for the loss value during training. But if you look at the validation loss, that's a pretty nice curve. That's what you would hope to see for your validation loss. So now let's actually we'll assume that that was a good training run. Let's actually run inference over this data set. So we'll increase the batch size. We'll say that we're going to use that same data set again. It's very typical, very common in unsupervised ML workflows where you train on the same data that you run inference on. And we'll call inference. And we'll get, some more information on the other side, what model we're using, the data set we're using for inference, et cetera, et cetera. Now, I want to go ahead and take a moment here and say, like, all of this results of inference is being saved as Lance file formats, which may be an unfamiliar format for many of you. Lance is a newish file format that is really well loved by the ML community. I think it's safe to say that. What it does is it performs very well in both full scan reads like Parquet does. It's a columnar data store like Parquet, but it also has very rapid random access reads, which Parquet typically struggles with. And so it can handle, picking and choosing random values, but it can also do sort of sequential analysis very easily and efficiently. So let's take a look. Let's start to dig in a little bit here. So I won't force you to read over the code here, but what I will tell you is that because we've stored it in our Lance format, Lance natively supports a vector database on the back end. So what that means is that it allows you to do very efficient similarity searches and distance searches between values. And so what's happening here in this code is for every sample that was run through inference, we are finding its 5 nearest neighbors, and we're taking the median of the distance to those 5 nearest neighbors. And by a distance to nearest neighbors, I mean the L2 norm for this 64 dimensional vector, right? So when we take the median of the distance to the 5 nearest neighbors and we plot a histogram of that, what we get is this sort of long tail distribution. And what you get from this is that many of these things are close together and similar in terms of how the model has evaluated them. But you have this long tail where some things are drastically dissimilar. So let's dig in a little bit. If we plot, I know, I'm sorry, plotting code's the worst. I'm going to scroll past the plotting code. If we plot those first 16, the first 16 images or objects from that histogram, these are the types of things that you see. So compact, relatively isolated in the field, not a whole lot going on. They kind of look just like a little blob in the middle. If you do the other end, the 16 on the far end of the tail, this is what you get. So extended objects, imaging artifacts, interacting galaxies, these sorts of things. Something, noticeably different, right? So let's see if we can exploit that a little bit. So I don't know about you all. I cannot visualize 64 dimensions in my head, but thankfully we have tools to reduce dimensionality. UMAP is one of those tools, and Hyrax has UMAP built into it. And so we can call hyrax.umap and reduce the dimensionality down to 2 dimensions very, very easily. And that's exactly what's happened here. So we've taken our 64-dimensional element results, reduced that down to 2 dimensions, and then again some plotting code. I'm sorry. We'll plot the 2D output from UMAP, and then we'll overlay the 16 closest and the 16 most distant objects. So the blue ones are the normal, the ones that are close to the average, and the red circles are the ones that are far out on the tail. And so you see here, there's some pretty distinct separation. Yeah, I agree. There's some overlap here with some of these, but this gets you far enough down the line that you could begin to potentially think about, well, how could you sort of chop off a section of this UMAP if a new sample came in and its result ended up in this part, maybe that indicates that it's an instrument artifact and that you're not interested in it. Whereas if it ends up in this part, maybe those are the emerging galaxies and you are interested in it. So I will stop there because that's getting a little too close to the actual sciencey side of it. But I think you can hopefully see, based on that, that Hyrax makes it relatively straightforward to piece this pipeline together so that you can actually get to the point of doing analysis and discovering things. So I'm going to jump back in to the talk here. This example is available in our documentation if you're interested in taking a look at it. Now, that was an example, and what I want to be clear about is that Hyrax is not hard-coded or specifically for unsupervised or image-based learning. We have quite a few different projects that are currently in flight. And I was just going to talk very, very briefly about a small handful of them. So very similar to what you just saw, image-based unsupervised discovery. This is an example of extragalactic science looking for galaxy mergers and evolution of galaxies. It's all unsupervised. It's all image-based. This is led by Ritra Ghosh. There's a paper in prep that's going to be talking more about it. We also have a project that's doing small body classification. So this is solar system science, and it is supervised with labeled data, and it is also image-based. And Max West, who's likely on the call, has been the main driver of this project, but it's related to KB Mod and some of the work going on there. There is a spectral-based supernova classification project as well, with Mi Dai and Liam Cunningham working on this one. So this is supernova science, also supervised, more clustering related, spectral based. We've worked recently with a group at UMN doing light curve alert classification. So this is it's basically a follow-up recommendation. It's multimodal. It combines time series data with images, with catalog data, with spectral data occasionally to do alert follow-up recommendations. So all that is to say, Hyrax has not been built just for unsupervised, just for image-based, just for extragalactic science. It is for many different things, many different things. If you're curious what it works on, yes, the answer is yes, it probably works on that. If you're curious if it applies to your science and you're interested in doing machine learning, yes, it probably does. All right, now some fun visuals. Visualization is hard. We've got some built in already. Here's an example of our built-in 2D visualization tool. It supports interactivity, panning, zooming, selecting, showing a random subset of images from a given selection. This runs in a notebook, so it's relatively lightweight. It's implemented using HoloViews and data shader. It's made to make it relatively easy for you to examine these sort of low-dimensional latent space representations of images, but also be able to quickly see what's going on. the information in the table can be exported so that you can select a particular region and then export the table so that you can work with it as a pandas data frame and do subsequent secondary analysis and those sorts of things. Um, in the interest of moving ahead, I wanted to show you this one too, because we've got this really sweet 3D visualization as well. It covers a lot of the same uh, uh, ground, but this one runs in the browser. It's implemented using Three.js. Um, Again, it's interactive, so you can pan, zoom, select. One of the nice features of this, in addition to um, being able to interact with it, you can pick and choose the different data facets that you use for coloring the points on the screen. So if so you can start to layer on additional dimensionalities, quote unquote, and interact with those. It also supports selection. So hopefully, well, yeah, there we go. Here's our little quick selection. And you get some images based on that. And then again, you can get sort of a tabular output of the fields that you've selected there as well. So very, very cool things. I do not want to minimize how much effort went into creating these visualization tools. I think they're absolutely lovely. All right, I'm going to pause on the going deep on things and go and sort of transition into just throwing a bunch of stuff at you because there are many, many, many features of Hyrax. And if nothing that I've said so far caught your attention, I'm hoping that at least something in these next few slides will, um, because they're a little bit challenging to demonstrate, but I'll just talk through them. HSC and LSST specific tooling. This is a lovely histogram of cutout acquisition time for LSST coad data. What you see here in seconds is the number of cutouts that you can acquire. The reason it is distinctly bimodal is because the person who implemented this did this in a very clever way using some very clever caching so that we can download full patches of data and acquire all the cutouts related to that very efficiently. So the vast majority of cutouts are acquired very quickly, whereas a few cutouts take on the order of 1 to 10 seconds to acquire. But most of them get cached, or at least the patches get cached, so you can very quickly acquire them. Similar story for HSC cutouts. Oh yeah, reduced dimensionality with UMAP. So like I was saying during the extragalactic demo, reducing dimensionality is very important, especially for unsupervised data sets. And often unsupervised data sets are the types that we will encounter, especially as data scale increases dramatically. So having direct integration with these sort of dimensional reduction techniques is very handy to have. Vector database reverse search is another thing that we support. We actually have 3 different types of vector databases that are competing with each other under the hood. Lance is the one that I demoed just a minute ago, but we also support Quadrant and ChromaDB. And all of these are local databases that can be spun up in real time that allow you to do these very efficient sub-millisecond queries in databases that have many millions of objects in them to get very rapid similarity search results. We export models to ONNX. ONNX is the Open Neural Net Exchange. This is a very common format for trained models to be exported into because ONNX is very light on resources, both hardware and software. Typically, the software dependencies are only the ONNX runtime and perhaps NumPy. Is a very common platform to use when deploying models to production. So a contrived scenario, perhaps. You train a model, you know that it performs well, you want to deploy it so that it will respond in real time to perhaps an alert stream. You can use this ONNX format to deploy a lightweight model that way. We integrate with TensorBoard and MLflow. These are 2 sort of industry standard tools that are great for metric acquisition and just model comparison. Everybody's got their favorite. TensorFlow and TensorBoard and MLflow are 2 of the sort of front runners. But what's nice is that Hyrax is already integrated naturally with all of these. We emit lots of metrics on the user's behalf already, and we've exposed methodologies within Hyrax for users to emit additional custom metrics if there's something specific for your model or for your data set class that's important to measure. You can have those recorded in MLflow or TensorBoard very easily without too much effort. All right, that was the whirlwind tour of the things that we've got. I'll talk just a little bit about the near-term goals, and then we can kind of go from there. Uh, the big ticket items for Hyrax for the next roughly 6 months is making sure that we are rock solid for DP2 scale and DR1 scale from LSST. So that includes doing things like benchmarking our internal storage system, supporting streaming data formats like streaming alerts or working with HATS catalogs naturally, and then revisiting our visualization because a lot of effort went into it, but we want to make sure that that's is really going to scale up to the levels we expect. We want to add more support for user code. So one is documentation. Documentation is hard, and if it's a little bit embarrassing, that's okay. But we're going to make ours better with more example code, clearer documentation. We really want to provide templates for projects that are using Hyrax so that people can create a templated Hyrax project within one command and get things set up and running even more quickly than maybe they already can. And we just want to work with people who are using Hyrax to identify where the rough edges are and see how we can make it a more natural experience, a more ergonomic experience for users. And yeah, we just want to work with more folks. Like I was saying at the beginning, Hyrax is getting into a pretty stable state, and now's the time. If you've got a machine learning project in mind, like come hang out and talk with us. Uh, right now, your voice is going to be louder than it might otherwise be at a later time. We really want to work directly with folks who are interested in working with Hyrax. And so, yeah, please join us. This is the last slide, I promise. Um, if you're on the Discovery Alliance Slack group, Link Frameworks Hyrax is our public channel. Feel free to join. You'll see all the chatter about Hyrax. If you're interested in joining a tech and science meeting, I think we've got one scheduled for next week. The Zoom link is here. Aritra Ghosh runs those, and it's wonderful. If you just want to check it out on GitHub, check it out on GitHub. It's right there. And again, this is the folks who've worked on it. So Samarth is our lovely intern who's been working with us since the beginning of the winter quarter. Aritra is our Catalyst Fellow and postdoc and has been helping out a lot and giving us standing in as a representative for all scientists and doing a lovely job at it. Michael Tarosso here on the call, who just lit up the camera here, has been the other primary developer, and then myself. So anyway, I'll stop there. Thank you all for your attention. I'm happy to take any and all questions that we got.
Thanks again, Drew, for an awesome talk today, and thanks to everyone for attending the talk series. We do have a little bit of time for questions, and feel free to raise your hand, ask in the Zoom chat or on the Slack channel. And Charlotte, starting with you.
Yeah, thanks, Drew. This looks really awesome. So I was curious to ask about, it seems like a really good framework for combining kind of either multimodal data sets or data sets from multiple surveys at once. Like you mentioned, if you have an LSST data set that you want to translate to Roman, it's a good way to do that. And I guess I was just curious, what would it look like if you had data from, maybe you had Roman cutouts and Reuben cutouts and you wanted to build a model based on both, or maybe you have both light curves and cutouts or something like that. How easy is it to kind of get that all to work together?
Yeah, great question. That is the goal of that Hyrax QL query language that I was talking about. So, in the interest of total transparency, there's a rough spot, and that current rough spot is that we expect your two data sets that you want to combine, or your multiple data sets that you want to combine, to be index aligned. So, if I say index 0, it needs to be from both data sets returning data from the same object, right? So that's the rough spot right now. We have some plans for one, integrating with HATS catalogs that can help make cross-matching much more efficient, and then we can stream that data in. We also have some maybe pie in the sky dreams of being able to do that cross-matching on the fly, doing those cross joins on the fly between the two data sets. So the ultimate goal is to get to a state where we don't require a user to have to create a tertiary data set if you've got two that you want to combine, you don't have to duplicate all
Right.
that data. Yeah.
Awesome. Thanks.
Yeah. Mm-hmm.
And we have a question in the chat from Douglas. Will the slides be available afterwards? I'll post them, or if you, yeah. Okay, that's a yes. Affirmative.
I intend to share. Yes. Yeah.
Okay, cool. Fantastic. I
Hey,
saw.
Yeah. Hi,
yeah,
Ashad.
thanks. Hey, great talk, thanks. I have a question. I have two questions actually. One is the backend PyTorch, or if I have a model in PyTorch, how easy is it to integrate my own model?
Got it.
Um,
Yeah. So short answer to your question, yes. Right now, the main backend is PyTorch. We leverage also PyTorch Ignite to do some of the sort of convenient functions. But yes, PyTorch is what we've based everything on at this point. We anticipate expanding that again as users say that they have a TensorFlow model, or as they say they have a JAX model that they need to support. This sort of stuff.
okay.
And for
And what about like training on parallel GPUs or multiple nodes even on a cluster?
Right. Yeah. So right now, Hyrax very naturally supports the scaling from laptop to department GPU to HPC with multiple GPUs. We don't have great support for multiple nodes with multiple GPUs.
Mm.
So we have, and the reason for that is that we have not yet had a user come to us and say, we need that. And when we have a user come to us and say, we need that, that's you, then we can begin to dig in and implement that in a nice, again, ergonomic way that makes it easy for you to do.
I want to add two quick things to those answers. If you've already got an NN module class in PyTorch, we basically export a decorator and we have you write one additional function. You already probably have a forward function. You're going to write one more function that is the inner kernel of your training step. And then the name, when Drew was showing those notebooks, he said Hyrax CNN in the config in one of them and Hyrax autoencoder. That's just going to be end up being your class name.
Mhm.
And that's how it's going to load it. And then also we kind of have some architectural plans around how we want to do multiple nodes. And again, we want to have some contact with someone who's actually trying to do it to make sure that those architectural plans are implemented in a way that actually works for real users.
Mhm.
So we've
Okay.
thought about how we're going to do it a little bit, but we want to make sure we're not sort of, building something that is, sounds useful or feels useful to us, but isn't actually useful for a scientist.
Mhm. Okay. Well, I'm not doing any now, but with Roman and Ruben coming online, I will need to probably.
Oh yeah, we're
Um,
pretty sure it's going to happen.
yeah, so yeah, if not me, someone else. But my last question was, I was just curious if you had like a built-in hyperparameter tuning sort of something.
Great question. So not built in directly to Hyrax because we have not settled yet on like what we think is the best hyperparameter tuning tool. We
Mhm.
have the hooks in place and examples of using like HyperOpt and RayTune, weights and biases. And so we have the tooling to do it, one for loop outside of Hyrax. And use Hyrax as the main driver that keeps everything organized, and then use the hyperparameter tooling
Mhm.
tool to actually drive it and search that space, but not directly built into Hyrax yet. So again, if this is something that you're interested in and going to be using, then we would love to collaborate and hear more about how you use it so we can figure out how to implement it.
Okay, thanks.
Mhm.
Right, we are right about at time, but remember, you're always welcome to type out any questions in the Link Tech Talks channel in Slack after the fact, and we'd be happy to answer them. Thank you again, Drew, so much for the presentation. And stay tuned for next month, April 9th, where we'll be having our next Tech Talk with me, Di, presenting simulation package like curved links. And Link Frameworks also holds open office hours during this time slot on weeks where we're not doing a tech talk. So you're also welcome to check out Hyrax, fiddle with it a bit, and then come into the office hours and ask any questions you have then and there. And then if you have any ideas for a future Tech Talk, we'd love to hear from you. So feel free to reach out to us on the Slack or by email that you can find on the Tech Talk webpage. And with the speaker's permission, today's Tech Talk will be available on our YouTube channel within the next few days. Have a great rest of your day or night. And thanks, everyone.
Thank you all. Appreciate it.